Good afternoon, everyone. Thank you so much for joining me today. I'm Bahador, a customer-facing data scientist with H2AI. As you can tell by the title of the presentation, I'll be talking to you today about a subfield of AI that's creating a lot of traction, especially in the last few years, called explainable AI. So what we'll be talking about will be, what it means to explain an AI model, why you should care about it, and if you do care about it, how you can go about achieving it in practice. My goal is that by the end of this 30 minutes presentation, you will have a rough sense of, what is explainability all about and what does it fit in your business. All right, so let's just dive right in. The first question you probably have is that, what does it really mean to explain an AI model? And the short answer I have for you, well, it depends. There's no consensus right now as to what it means exactly, and there are a few reasons for this. First of all, it depends who's asking for explanations and what's their intention. For example, if you're an AI expert or a data scientist who's trying to develop a model, you're trying to debug your model, and let's say you're developing an image classifier here, you might be interested in figuring out, okay, I'm using this deep neural networks, what is this certain neuron in certain layer doing, and what is it responding to, which happens to be, for example, a certain wheel in input image, and you're like, okay, what are the kind of wheels this neuron generally responds to, right? So things like this are important for you because you're trying to understand what the model is doing, how you can go about improving it. On the other hand, if you are, somebody who's just examining the model, you're like a regulator or something, the kind of explanations you're looking for might be, trying to figure out how the model output, which is the prediction, is related to its input, right? So imagine there's an example here, a tabular model, it's a model that's running on tabular data, trying to predict something is poisonous or edible. You can get a sense of, okay, these are the features that the model is looking at, and this is the contribution of the features, right? At the bottom, you have a similar situation for an image classifier. You might be interested to see, okay, what are the pixels that the model is looking at to call something a dog versus a guitar, for example, right? These are the two general flavors of explanation you come across if you do explainability. That being said, though, there is sort of a fundamental trade-off in terms of complexity of explanations versus the, what's called interpretability. Basically, what it means that for any given situation, you have an almost infinite spectrum of explanations you can provide, from very complete, very accurate, all the way to very interpretable, very easy to understand. To make it more concrete, let me give you an example of it. Imagine you are a data scientist, you develop an image classifier in a company, and then you go to a CEO, you're trying to explain how it works. You can give them a very interpretable explanation that says, okay, I'm using deep neural networks under the hood. That kind of helps. Or you can tell them, you know what, I'm using the inception, architecture under the hood. Go check out the paper that explains how it works, right? They're both valid explanations, but none of them are really helpful for the CEO person here, because what they really need is something that's kind of in the middle, right? Something that has enough information that tells them something more about the model, but it's not too complex for them to understand, right? And that's a very important consideration when you're doing explainability, to kind of match your explanation to your end user's needs and level of complexity. The third component here, which doesn't get talked about very often, is that fortunately or unfortunately, most of the explainability endeavors in the explainability field has been driven by experts of AI, and we might be risking a situation which Tim Miller calls inmates running the asylum, which is basically drawing an analogy to what happened in the software world back in the 90s and early 2000s, when you had really good software with very crappy UI, right? He's basically saying the same thing is happening to AI explainability. We're trying to explain to people how our models are working, but we are not doing a good job because we're doing explanations for ourselves as experts, right? We should start to look into how other fields of science like psychology and sociology have been looking at this topic and what their finding was, and to our explanations according to that. One of his major findings in his paper is basically that social explanations that people tend to use are contrastive. So they basically are about why event P happened instead of event Q, and not why event P itself happened. They're not necessarily causal. That's a very important basically finding he has, and things like this could completely change the course of the field in the future. So that was, basically a very quick overview of the what of explainability. Let's talk about why you should care about it. I feel like everybody who's in this room already kind of care about it because that's where you guys are here to hear more. But if not, you can go to Google right now and just look for the term explainable AI, and you definitely come across a whole bunch of articles, some of them being published by very credible news outlets like Harvard Business Review, and they're just saying we need explainability right now, right? There's all kinds of reasons they come up with, right? And you might say, you know what, these are just kind of one-off articles, doesn't really mean much. Well, you can go to Google Trends, right, just machine learning itself for this, and look into the upward trend of explainable AI over the course of the years, right? There's definitely something happening in terms of the interest of community in this problem. right? So let's talk about, given that you kind of agree with me that something is happening, let's talk about what are the drivers for this, rising interest. The first one that I personally see coming up very often is the notion of trust. And the idea is that very simple. If you want to trust these complex black box models we're developing, we need to understand them, right? And with understanding comes trust, and then you can adopt them and everything. And that's true. However, there's a big catch here, and that's something, that's not very obvious, something called the illusion of exploratory depth that's being studied heavily, by cognitive scientists. And it's a phenomenon that people tend to, overestimate or overgeneralize understanding of a complex phenomena if you give them some sort of explanation for it. And this could be very dangerous, not just in theory. In practice, there's, for example, this case study of, this model that was in production doing fraud detection. And when people were given a whole bunch of explanations as to how this model was operating, they start to trust the model prediction, even when the explanations themselves didn't add up. Even when the explanations were wrong, people still just blindly trusted those. And the authors of this paper conjecture that's partially due to the phenomenon I just told you, right? Illusion of exploratory depth. So basically what this means for us as people in this field is like, when you end up, present these explanations to people, you have to be really careful not to create trust when it's not worthy, right? Not to have misplaced trust situation. That's very important to consider. The second reason I see explainability coming up very often, especially in if you're operating in verticals that are highly regulated, like finance, insurance, and banking, is that there's already a body of regulation that's asking for explanations. For example, in the States, there's something called Equal Credit Opportunity Act, which is basically asking all the lenders to provide explanations to the applicants that tells them why the certain application was accepted or rejected. They call it the reason code, right? So it's already mandated by law. Or in Europe, there was a body of regulation recently introduced called GDPR, which is mostly about data privacy, but there are definitely clauses in there that arguably create a rightful explanation for models that are being put in production, right? So there's more and more regulations being put around this every day, and that's definitely creating a lot of interest in explainability because if you have to have it by law, if it's mandated, you better have a solution for it. The third reason, which is not maybe very obvious, is that oftentimes nowadays everybody's so focused on getting higher and more performance out of their model, right? Implicitly, what we're assuming is that to validate a model, the test performance is good enough. However, some of us are kind of forgetting that what we have with machine learning is basically models that are not learning causal patterns, right? They're learning associative patterns, and the danger there is that you could have spurious associations or correlations that the model is picking up on, right? And explanations are pretty good at revealing those kind of associations. A classic example is this example of a husky being misclassified as a wolf, but it's image classifier. If you just look into this as a person, you're like, okay, you know what? It kind of makes sense. Husky and wolf are kind of similar, so it's no big deal. However, if you look into the explanation as to what the model is looking at, you see it's not even looking at the husky. It's picking up at the background snow, right? So that will tell you there's something wrong going on with this model. You got to go back and fix before putting it in production. And of course, there's so many other reasons you probably have seen, things like potential for detecting bias in models because you can figure out whether or not certain protected features are being mistreated by the model through explainability. Or even being able to hypothesize about new knowledge. If you're in empirical sciences, let's say biology or medicine, explanations can be literally the starting point for developing new theories that you can go to the lab and validate, right? And last one that's, again, fairly new but very interesting to me personally is the tight interconnection of model explainability and model robustness. Right now, they're being studied as two separate fields, but they seem to be highly, highly correlated and tightly coupled. For example, there's some recent studies that shows that you can use model explanations to detect adversarial examples, attacks onto the model very successfully, without necessarily knowing what type of attack you're dealing with. You also have the flip side of this. There's studies that shows you can use explanations of models in terms of, in this case, the training samples that are useful for prediction to actually craft adversarial training samples, right? So that shows you right there that there's definitely this tight connection. You can go from one side to the other, and these two problems should be studied together. All right, so that was basically a quick summary of what it means to explain something and why we should care. Let's talk about how we can go about achieving it. When people talk about AI explainability, generally the implicit assumption is that we're talking about something called post-modeling explainability. So there's a model that's already pre-developed. Now you're trying to extract explanations that will tell you how it's operating. However, the principle of explainability is something you can actually apply to the entire AI development pipeline. So you can do it, of course, before the modeling stage to understand your data. We're going to see how it works. You can apply it during the modeling phase, ideally, actually, to have a model that's explainable and performant. And of course, you can do post-modeling explainability, which is something we do right now. And like I said, the main focus of the field so far, at least, has been post-hoc explainability. So let's talk about the pre-modeling explainability, see how we can go about achieving it. The most common way people go about this, as some of you guys might already be very familiar with, is the notion of exploratory data analysis and visualization, emphasis on the term visualization. And here's a classic example of why visualization is so important in practice. These data points or data clouds all have the same mean and standard deviation. However, if you were to visualize them, you can see they look very different, right? So there's something definitely in your data that no statistical number can actually necessarily tell you. You have to literally see it. And you might say, what if my data is very complex, very high dimensional? Well, in that case, you have all kinds of good options available to you right now. Things like parallel coordinate plots, or things like different dimensionality reduction methods like PCA, or more advanced methods like TST, and even recently UMAP, right? They're very powerful techniques you have in your disposal right now. They're open source, by the way, that you can start to use to understand your data better. The second category of pre-modeling explainability methods are a set of proposals by people who are kind of worried about the gap that's between people who are collecting and curating data and people who are actually consuming it, which happen to be data scientists, machine learning people. And because of that gap, we have a lot of cases of data being misused or abused. What they're trying to do is they're trying to bridge that gap by proposing ways of publishing data sets in a standard way. So when you get a data, as a data scientist, you get a data set. You know what it looks like, you know what was the intention behind it, you know what you should or should not be doing about it, right? It's just like when you go and buy a car, generally it comes with like a manual or something, right? They don't just give you the complex, Mercedes S-Class and expect you to know how to operate it, right? The same thing should be happening for our data set, right? We should have a standard way of describing them. So there's more interesting work being done in that space. Here, this one is an example of a project called Data Nutrition that came out of MIT Media Lab last year. They're trying to achieve something similar. The third way you can go about pre-modeling explainability is the notion of data set summarization. Again, there's works here and there on this, but I try to make it very clear. It's very useful for understanding your data, especially if you have a large data set, because what you can do with this, instead of looking at all the data set, which could be massive, you can look into the most common patterns in the data set, let's call them prototypes, and also look into the kind of rare cases that are not outliers, that are still useful, let's call them criticisms, right? And through that, you can quickly understand how that data set looks like in general. Here's an example of a prototypes and criticisms for the MNIST data set. You can see by looking at these examples only, you can pretty much understand what MNIST was all about, as opposed to looking at, let's say, 10,000 samples or something, right? So it's a very useful technique in practice. The last one is also the one I personally again like a lot, but still it's more in sort of a researchy stage right now, is the notion of doing feature engineering, but doing it with features that are explainable. And the main reason is if you have a model that's very powerful, very predictive, but the features it's using are not explainable, even if you explain that model later, that explanation is not very useful because you don't really know what the features mean, right? So you want to make your features explainable. There are two ways to go about this. Is either you can use your domain knowledge to craft features that are explainable and useful, or ideally you want to use AI itself to do that. And that connects to a field that's growing rapidly called disentangled representational learning. When you try to use generative models that would allow you to describe complex data, let's say in this case images of 3D chairs, but not do it with, let's say, pixels, but do it with these three features of azimuth angle of the chair, the width of the chair, and the leg style, right? So imagine if you can capture or represent your data this way and develop models through this, it's going to be a lot more easier to understand what's going on. Well, like I said, this is a field that's still being heavily studied and definitely not quite ready for prime time. All right, so we talked about pre-modeling. Let's talk about how we can go about making our models more explainable. Well, traditionally what this means, some of you might have tried it already, is that you're kind of limiting your choice of models to models that are deemed more explainable, things like linear models, decision trees, the traditional case-based reasoning methods, and so on and so forth. What happens, though, generally because of this, because your choice of models is limited and the models are relatively simpler, you have a performance penalty, right? So the explainability is high, but the performance is lower. And this has got some people, like this diagram here taken from the explainability project at DARPA, to think that there might be this sort of fundamental trade-off between explainability of models and their performance. However, there's more and more works coming out there that kind of prove that's always not necessarily true. And the reason we end up with this situation is because we develop our models without even considering explainability. Now we all of a sudden want to fix it. I'll give you two examples of methods that allow you to fix the problem, to a certain extent, of course. The first ones, I call them hybrid architectures. For example, here is this one called deep KNN, when you combine a deep neural network with a k-nearest neighbor architecture to do image classification. So the idea is that you use the deep neural networks for what they're really good at, learning good representation of your training data in this case, but you don't use them for testing or inference time. You actually use a k-nearest neighbor on top of representations that the deep neural network learned of your training data, and you do inference through that. And the authors show with this simple trick, you can actually get a very powerful image classifier, which is also explainable and also even more robust to adversarial examples. So you can see these adversarial examples of a panda. When you make it like an adversarial example, you can clearly see how the model gets confused throughout the inference process. So it's very easy to detect that kind of adversarial example and remove it if you wanted to. So very promising line of work. The second way you can go about having models explainable is to train your models to produce not just the predictions, but also explanations along with it. So one of these examples is this method called TED that was proposed by researchers at IBM last year, when they show how you can turn the supervised machine learning process all together to make it produce predictions and explanations combined at the same time. And they got very good performance out of it as well. All right, I definitely want to talk more about explainable modeling, but because the bulk of literature is post-hoc explainability, let's spend some time on that and talk about how it looks like. So again, it's kind of like if you look into like articles out there, there's lots of methods for doing post-hoc explainability. It's almost like the literature is being littered by these methods. So instead of talking about all of them and I guess bore you guys with, I kind of propose to talk about sort of this taxonomy that kind of reveals the underlying structure of all these methods. So the idea of this taxonomy is that all these post-hoc explainability methods have a target which is what they're trying to explain. Let's say the model prediction, have a set of drivers, which are the things we deem as the causal factors of the target, let's say input features of a model. And then you have, of course, the explanation itself. And because explanation is just a piece of information, it has a structure to it, right? Let's call it the family of explanation. And lastly, you need a way to obtain your explanations. Let's call it the estimators, right? So let's talk about each of these components of methods in general, so you get a good sense of what does this feel all about. Starting with the targets, of course, right? So the targets of explanations are the things we're trying to describe. I talked about understanding the inner working of a model versus input-output relationship before. So these are the two major type of targets. The other thing you have here is the scope of the targets could vary. You could have a local scope when you're trying to understand things at the local level, let's say for instance prediction, versus at the global level, let's say for all instances of a certain class, how the predictions are coming about. And lastly, you have the one that's maybe not very obvious, is the complexity of your target, right? So oftentimes the examples you see, we have a simple target that's like a numerical number of a classifier, or like a regression model output, but it could be much more complex. It could be like a sequence of labels or words that its translation model is spitting out, right? In that case, the traditional methods you have don't really cut it. So in the example on the right-hand side is actually taken from an approach that was proposed to explain a translation model. You can see the family of explanations they picked is actually something called a bipartite graph, right? So on one side of the graph, you have all the input words of a translator. On the other side, you have all the output words, and you're showing how they're interacting with each other through this complex, basic explanation family, right? The point is, when you want to explain your model, just be careful, what your target is and how complex it is, because that's going to impact your choice of methodologies. The second aspect of this taxonomy are the drivers, like I said. The most common drivers you see out there, of course, are input features. Whatever goes into the model, let's see how it's impacting the output. But more recently, you have more cool options like the training instances, right? There are methods like influence functions that can allow you to, in theory, figure out what are the training samples that thought model to make a prediction for this certain instance. What were the training samples that were helpful or hurtful? And also you have even more interesting stuff like TCAF proposed by researchers at Google last year, which allow you to attribute how certain concept is even contributing to a certain prediction, as long as you can define that concept with a set of examples. So here what you see is that we're using TCAF to see whether or not the stripiness pattern that we're representing by these samples on top left is contributing to the prediction of images of a zebra by an image classifier, right? It's a very powerful idea because if you have if you suspect your model is responding to certain concepts that are not part of its feature space, you can still test it out with this approach. Actually, Google is investing a lot of money in this methodology right now. All right, the third component, of course, is the family of explanations, right? What is the structure of explanations you're dealing with? So, of course, you have the traditional importance scores that most of you guys have probably seen, but you also have other options like decision trees, dependency plots. So you can see here, when you have your model output, you pick a certain feature that's important to the model output, you change that feature within its range, and you see how the prediction varies, right? And then you can compare the way model behaves to your domain knowledge to make sure the model is doing the right thing or the wrong thing, right? So that's very important to validate your models. You also have counterfactual explanations, which basically tell you what is the minimum change you need to be making to the input to this model to change the prediction. Let's say your loan got rejected by this, this model. How could you go ahead and change your behavior as a person so next time around your loan gets approved, right? So it's a very actionable type of explanation that we can have. You also have verbal explanations, bipartite graphs, and so many other family of explanations that you should kind of pick and choose based on the application you're dealing with. And lastly, the last aspect are, of course, the estimators, right? So how we can go about actually obtaining our explanations. Some of these methods are model agnostic, so you can apply them to any black box model, at least in theory. Some of them are more model specific, which generally means you can apply them to neural networks. The other source of variation here is the underlying mechanism these methods use. Some of them use the so-called perturbation mechanism. So the idea is that with perturbation, you have a model that has an input, let's say it's image classifier here. You segment that image, and then you start to perturb those segments to generate a whole bunch of other examples, right? You feed them through the model, and then you feed a linear model to those predictions. The coefficient of that in the linear model tells you something about what were the most important segments that help model predict, let's say, this image as an image of a frog, right? This is actually exactly the mechanism that the well-known LIME approach uses under the hood. And so many other methods use a variant of this technique. The second common type of mechanisms we have is called backward propagation, which is almost like the reverse of perturbation in the sense that you start from the model output, you work your way back by coming up with the contribution of different neurons to the model prediction layer by layer until you reach the input layer, and then when you're there, you have your explanation, right? These methods are generally only applicable to neural networks, but we have so many different flavors of them based on how you define the contribution of neurons, how you define the relevancy, and so on and so forth. And of course, we have methods like proxy, or surrogate methods, when you replace a complex black box model with a simpler, let's say, decision tree. And lastly, we have activation maximization methods, which you normally use when you're trying to explain the inner working of a model. Let's say you pick a neuron of a neural network, right? You optimize the input to the neural network, you optimize the input image to the neural network, so you end up with an image that will maximally activate that neuron, right? And that's supposed to tell you something about what that neuron's role is within that architecture. All right, so I give you a very high-level overview of explainability in general. Because I'm from H2O, I'm going to talk to you about what is happening in terms of interpreting at H2O. We are arguably one of the pioneers of AI explainability in industry. We've been incorporating explainability in our products as of 2016 for 3 years already. Patrick Hull, who is basically the senior product manager behind our machine learning explainability or interpretability, has published an O'Reilly book when he summarizes his vision around this. I encourage you to check out his book. It's very interesting. Right now, we're working closely with our clients, with industry regulators. We're trying to establish best practices of explainability in industry as well, based on our learnings. And just a quick bit about our H2O as a company. We started off as an open source company back in 2013. Some of you might have already used our H2O library if you want to do machine learning at scale. That's one of the go-to methods out there. So what you can do with H2O, you can actually do machine learning at scale with big data ecosystems like Hadoop and Spark. More recently, however, we're kind of venturing into the AutoML world with our enterprise software called Driverless AI. And what Driverless AI is meant to do is meant to streamline most of the tasks that a data scientist does on a day-to-day basis. Starting from data collection, you go and then visualize your data very quickly, you understand it. Then the task of feature engineering, algorithm selection, algorithm tuning, all that stuff. Driverless helps you speed up the process a lot. You can also customize all the steps you want. And once you're done, you're happy with your model, you can quickly package it up, make it deployable. And you get nice, automatically generated documentation for you. And of course, you get the machine learning interpretability to help you understand it more, which I'm going to talk about in a second. So machine learning interpretability is basically like another, imagine it's like another pipeline within driverless that you run on top of a model that's being developed. And once you do it, you get this sort of nice dashboard that gives you all kinds of different type of explanations to help you understand how that model is behaving. So you have, you have the feature importance type of explanations, you have decision trees, you have partial dependency plots, and so on and so forth. And our clients are generally very happy with this because, especially if they're in industries like finance or banking, because they need this stuff already and it helps them trust the models that they want to put in production. What's also cool about MLI, you can also apply it to models that are developed outside driverless. So it's not, doesn't have to be used only within driverless itself. Okay, so that was pretty much all I want to share with you in terms of what's happening with explainability. I'm going to share with you now sort of the way I see and hope the future of this field is going to evolve. The first thing I'm hoping is going to happen is that I hope people in this field start to infuse learnings from other disciplines of science, let's say cognitive sciences and social sciences and so on, into the models and the explanations they've developed. Because at the end of the day, we are dealing with people. We have to understand people to be able to explain stuff to them, right? So things like contrastive and counterfactual explanations that people tend to prefer, we got to spend more time developing those kind of models. The second thing I'm hoping is going to happen is that I'm hoping we'll see like an emergence of explainable AI best practices to be, to happening over time. So things like go-to explanation methods. Things like SHAP, for example, is an approach a lot of people use nowadays. I hope more and more methods will show up. Also, more of a refined and new set of regulation around explainability, right? Because we don't have enough of them right now. I'm hoping it's going to come up. And last one is evaluation procedures for explainability are very ad hoc right now. We definitely need to make them more well refined and established. So overall, we have the field that's more mature, more actually ready for real life scenarios. And beyond all this, like I said, the focus of the field so far has been on post-hoc explainability. But I'm convinced that the future of explainability is on doing explainability by design. So things like explainable feature engineering or having more and more architectures for doing explainable experiment modeling is going to be the future of the field. If you're interested to learn more about these ideas specifically, I'll encourage you to check out a Nature article that came out. It's written by Cynthia Rudin, one of the pioneers of explainability, when she lays it out for everybody. Like, why is it that we shouldn't be doing explainability as a post-hoc exactly? Why there is hope for explainable modeling? And what are the ways you can go about doing it? She tries to convince everybody that's the way to go. So I highly encourage you to check it out because that's the way to go. And most of the content for this talk is based on some of the articles I've already written. They're all available online. If you want to learn more about these ideas, please feel free to check them out. And that's about it. Thank you for your attention.